Hello. We're going to be talking about Chapter 15 from the second edition of the Top Hat Organic Chemistry textbook. This one's going to be dealing with NMR spectroscopy, or nuclear magnetic resonance spectroscopy. So this is actually the basis of the technology for MRI machines. But that it actually used to be called nuclear magnetic imaging, but people didn't like the idea of putting their head in something that says nuclear, even though in this case the nuclear actually deals with the nucleus, not necessarily nuclear radiation. The marketing wasn't good, so they changed that to MRI, and so the names diverged, but it's the same technology. And so for this one, like all the other spectroscopies, what we're going to be doing is we're going to be putting light waves through our sample and seeing how the light changes. Okay, so we know it goes in, and we'll measure how it comes out. Something like that, like all the other spectroscopies. In this case, we're actually going to be using radio waves, so very, very long wavelength waves. The other thing that we're going to be doing is we're going to be putting that into a giant superconducting magnet. Okay, and so your sample is actually right here. It's going to be in a thin tube. It's going to go down into this into a magnet of very high strength, something like that. So it's actually superconducting. So it's sitting in a pool of liquid helium at about 3 degrees Kelvin, or 3 Kelvin. And so and from there we're going to be shining the radio waves onto it. Okay? The signal that comes out is actually going to be is going to look like this, where we're going to have these sharp peaks coming up from the bottom. So here we're going to be looking, unlike IR, which goes down, this one goes up. So in order for us to be able to do this, work with this, the nucleus has to be magnetic, and not all nuclei are magnetic. Okay, so what we need for magnetic isotope is either an odd number of protons and or an odd number of neutrons. Okay, you can actually both be odd. That's fine, but you at least need to have at least one of them be odd. Okay, so here, hydrogen, right, it has an odd number of protons, so we're fine. So it's magnetic. Fluorine, it has an odd number of protons as well. With that, so it would also be magnetic. For something like oxygen, we have an even number of protons and an even number of neutrons, so so it's not magnetic. Okay, so we aren't going to be able to look at oxygen 16 inside of an NMR, but we would be able to look at hydrogen, regular hydrogen, and fluorine 19. Okay. Now, when you have a magnet that's spinning, you're going to, or a charge that's spinning. Okay, you're going to create a magnetic field. Okay, and those protons, as they're spinning, they'll either have a spin with a magnetic field going up or down. Okay, and so just like we have like a north and south magnet. Okay. Now, when the sample is just sitting there, when your molecule is just sort of sitting in a tube, the orientation of that, of the magnet is going to be sort of random. Okay, but once you put it into a magnetic field, a strong magnetic field, what's going to happen is the spins are going to line so that its magnetic field is either going with the magnet or against the magnet. So you can sort of think about, boats. In this case, you can sort of think of boats in a lake, right? The boats are going to be kind of going all in random directions. Okay, but you take those same boats and you plunk them into a river. Now they're pretty much either going to go with the current or against the current. They're not necessarily going to be going a whole lot of side to side. Okay? Something like that. So now, if you're going with the current, right? So if your magnetic field is going with the the direction of the magnetic field, it's going to be a lot easier. Just like if you're trying to, if you have a rowboat, you're going to be going with the current. It's going to be a lot easier. If you're going, but you could technically go against the current, right? Go upstream. That's going to be a lot harder, so it's going to require a lot more energy. But that is one of the states you can do. Okay, and it's this gap between when you're going with the field or you're going against the field. That's what we're going to be measuring with the spectroscopy, with the NMR spectroscopy. Because what happens is, if you get a photon that matches this gap, okay, what's going to happen is the photon is going to come in, give this nuclei enough energy to get into this state here to start going against the field. But this high energy state is not stable, and so it's going to say, wait a minute, I want to go back down. When it does, it has to release the energy, and it releases the energy as a new photon, and so we're able to detect that. So what we're really doing is we're measuring that gap there with radio waves. Okay. Now, one of the things we have to do is we have to learn about how the signals are produced. And in order to be able to produce a signal, okay, you have to be chemically distinct from the other hydrogens. Okay, so what we need to do is we need to learn about hydrogen equivalence. Okay, so if a hydrogen, okay, is chemically equivalent, those are going to act as a set of hydrogens. Okay, and they can actually be on different hydrogens. We'll talk about that in a minute. Okay, so each set is going to give its own signal. Okay, so we need to learn how that's going to happen. Okay. So what you can do is you can say, okay, I'm going to redraw the molecule where each one of the redraw the molecule where I'm going to replace one of the hydrogens with an X. Now, is there a way so how do I compare two versions of the molecule where, can I turn or rotate the molecule so that it goes back to the other one? If I can, then that means that those two hydrogens are equivalent. If the relationship between the two molecules are that they're enantiomers of each other, then again, those hydrogens designated by the X's, those two X's, are going to be chemically equivalent. If instead they're going to be either constitutional isomers, they have no bearing, no relationship to them, there's no way that I can rotate or flip or whatever the molecule to get this molecule with the X to look exactly like this molecule with the X. That means those two hydrogens that we substituted for the X, those must be they must be different, or if they give a diastereomers. Okay. So lots of examples here. So the easiest one to think about is if you have something like benzene here. So we're going to replace one of these hydrogens with an X, and so you can sort of see this as we're going around, right? So X, 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 that, right? So each one of these structures are going to have one of the X's swapped out, or one of the H's swapped out for an X. So if you look at these two molecules, right, I can just take this one and rotate it so that it looks exactly like this one. That would mean that these two hydrogens represented by these H's are equivalent to each other. Same with this one, right? We can just take this molecule and rotate it 120 degrees like this. It's going to look exactly like this. So that means these two hydrogens are chemically equivalent. Again, for this one, if you look at these two, if we just take the molecule and flip it over like that, this molecule is going to look like that. And so that means these two hydrogens are equivalent to each other. And you can go through all 6 of them, and it turns out all 6 of these they're what are called homotopic. They are all chemically equivalent. Okay, and so the NMR is going to see all 6 of those as a set, and you're only going to get one signal out that represents all 6 hydrogens. Okay. If we look at something like this, again, right, so if you look at the hydrogens here, right, we draw in these hydrogens. Like that. So if you look at the red ones, okay, and we're going to substitute an X for each one of these, so we have 3 of these, okay, I can simply rotate around this bond here and here to get back to this structure. So that means each one of these red ones is going to be a equivalent to each other. Okay, so these red ones are going to be a set. They're going to give a single signal. Okay. If instead we look at the blue ones, if we compare, you know, an X here versus an X here, if we compare these two, right, these two are enantiomers of each other. Right, so this one, you know, this one would be the S, and this one would be the R if you wanted to do it like that, something like that. Oh, actually, well, depending on how you do it, right? One would be the R, one would be the S. And so, since the relationship is that they're enantiomers, that means that these hydrogens, these 2 hydrogens here, in the blue, up here, are equivalent. The ones in the green here, okay, actually these 2 are also equivalent, or excuse me, these are also equivalent because the relationship between these 2 molecules here with where the green X's are, those are also enantiomers. So that would mean the green hydrogens are equivalent to each other. So we would have 3 distinct sets of hydrogens. And so we would expect to get 3 different signals out from our NMR spectrum. Now, they don't have to necessarily be on the same carbon, right? Because if you look at this one, okay, we draw on these hydrogens here. If you look at the red ones, okay, if you compare these top ones, right, we can just rotate around, you know, we can just rotate around that bond here and turn these structures into here. For here, if you look at these 2, all it is this thing flipped over, the structure just flipped over. Okay, so I can turn this guy into that one by just doing a flip. Here you would rotate the bond and flip. That's fine. But it turns out, because there's some symmetry in this molecule, all of these red ones, all of these red hydrogens would act as a set, and they would give a single signal that represented all 6 hydrogens. Same goes down here with the blue ones. Okay, these 2, right, I can just flip over the molecule, and this one turns into that. Okay, so that means the blue ones are equivalent to each other. And so we would get a signal that represents the blue hydrogens there. Okay. So you can have equivalent hydrogens on different carbons. Okay. You can also have non-equivalent carbons on the same hydrogen. This is one of the classic cases where if you compare right, so if you compare the red one to the blue one to this green one here, right, there's no way that I can flip this molecule to get it to look like this, where the X's would be in the same place, because there's no free rotation around this double bond, right? It's locked into place. Okay, so there's no way that I can flip, right? So if I were to flip it over to get the X in the correct position, then the chlorine would be over here instead of over here. Same thing with this one. If I tried to get the flip it over to try to get the green one in that blue position, now the structure would not be right. So the structure would be more like this. Right? The X would be in the wrong, or the chlorine would be in the wrong spot. Right. So if I flipped it over, it would look like this, and these are not exactly the same. Okay. So each one of these hydrogens are distinct, and it's caused by the fact that there's no free rotation around that bond. So if this was a CH3, right, and a single bond and a CH2, then we'd only have two signals. We'd have the CH3 and then this CH2 here. But since we're locked into place, we would get three distinct signals, one for each of the distinct hydrogens. Now, one of the reasons for this is because the time scale for NMR is very, very slow. Okay, something like that. And so we're talking about radio waves, which have a really long wavelength, and so they take a long time to get peak to peak. Okay? And so this bond rotation is going to be a lot faster than the photons going through it, than the speed of this NMR. Okay? And so they kind of blur together. So if you look at this one, right, so these are chemically equivalent here, so these three would give a single signal right there. This hydrogen here would give this signal here. Okay. Like that. So, and the because of this free rotation here, all three of those are morphed into a single signal. Now, this can actually become important if you're looking at something like a cyclohexane, where they are, even though they're on the same hydrogen, they are chemically distinct. In a way, they are, right? Axial versus equatorial, right? But you can, but the problem is with these two, they are flipping back and forth so quickly that they blur out. And so you can't see the two. Okay, so in order to be able to do this, what we need to do, because this is so fast, the thing to do is we need to slow it down. And so the best way to slow things down chemically is to cool them, right? Because temperature is just simply the average kinetic energy of a molecule, right? So if you lower the temperature, what you're doing is you're essentially measuring the fact that you're slowing things down. Okay, and so if you look at this, what can happen is at 0 degrees C, they would get blended together. But as you slow these things down, get down to -90, right? You can start to see the difference between these two samples pull apart, because now it's spending, one hydrogen is spending enough time in the axial position versus equatorial that it's on the time scale, so we can start to see these individual details. And so if you want to get finer details for these NMRs, lots of times what you can do is cool them down, okay, to see the individual hydrogens. Now, where these signals appear, okay, is dependent on the neighborhood they're in. Okay, so remember for IR we had distinct regions for the different signals. That's the exact same thing here. Okay, and what we do is we read it actually from right to left. Okay, this is sort of it's a legacy of when this was first starting out, how they needed to do this, and so nobody ever really got around to changing it. Okay, but what we do is we have it relative to the molecule trimethylsilane, which I'll show you in a minute. And so what we're going to say is, how far away are you from this TMS signal? Okay, and this is the units are parts per million. Okay, because the signal is in megahertz. Okay, and these shifts are in hertz. Okay, so it's how many hertz per megahertz is essentially what we're saying is this gap. Okay? And so it's typically shown by a lowercase Greek delta. And so you'll also see when we talk about upfield, okay, that's typically to the right. If we say downfield, it's going to be to the left of the spectrum. Okay, so this is the reference compound. So it has 12 equivalent hydrogens to it, right? Because I can rotate the molecule, and it comes in there. And so these guys are. It doesn't take much to get a good reference signal, right? We just need a little bit in there, so the NMR says, that's where 0 is. Okay. The other thing is the presence of the silicon also allows it to be shifted a little bit farther afield than normal carbons, and so it can kind of get out of the way of an all-carbon compound. Okay, and so that's what makes it good, because we don't want to have this overlapping with the carbon, with the signals on our samples. And since silicon's usually pretty rare, rarely incorporated into a into an organic molecule. And I know people are saying silo-protected groups, things like, yes, I know, but we can take that into account. But for most molecules you're going to be dealing with, especially in this course, they aren't going to have silicon in there. So it can get pushed down or upfield enough, so get out of the way, so you're not having to figure out which is your signal versus what the reference signal is. Okay. And so what we're doing is remember, we have this external magnetic field. Okay, and so your molecule is definitely feeling that, but it's also feeling the little tiny magnets that are in the nuclei neighbors, right? Stuff like that. So if you have a house, right, and the you have a house, it's in a little subdivision, really nice. If all of a sudden your so you have the property value of your house. If your neighbor, right, suddenly decides to start selling cooking meth next door, well, that's going to, you haven't done anything to your to the value, you haven't done anything to your house, but the fact that your neighbor has now started doing a drug house, right? So that's going to lower your the value of your house. Same thing here. If you the environment in which your the atom is present, okay, is going to make that particular nuclei feel the magnet a little bit differently. Okay, so it's not just the big magnet, but it says those changes away from those small differences from the magnetic field of the nuclei that's next door. Okay, that's where it's going to show you, that's where it's going to shift. And it's those minute differences that's what's causing the signal to be where it is. Okay, and so if you are next to, say, electronegative atoms, okay, it's going to push this, it's going to cause you to feel, because you're going to have less electrons around you, right, because the electrons are going to get sucked here, you're going to feel that magnetic field a little bit more, and so your signal is going to be a little bit further downfield than something, say, these red ones, which is is nearby to the oxygens, but not directly attached to them. Okay, so it's going to be feeling, it's not going to be feeling that external magnetic field quite as much. Okay, it's going to be what's called shielded. Okay, and so you can look at this, and then TMS we just set at 0. So what we can do is we can look at these distinctive regions. Okay, and so if you, now this doesn't have to be a CH2, it can be a CH, CH3, whatever. These guys, so if you're just a regular alkane, right, you're going to be in this region from about 0.5 to 1.5. In the 2 region, you're typically going to be next to something like arene is a benzene or a nitrogen or sulfur, or you're hanging off an alkyne, or you're going to be next to a double bond, either a carbon-carbon or a carbon-oxygen double bond. If you're in the sort of 3 to 5 region, you're typically directly attached to something very electronegative. So it's either going to be a halide or it's going to be an oxygen. They typically are in this 3 to 4.5 region. If you're hanging off a carbon directly off a double bond, as opposed to being next to a double bond, if you're hanging directly off of an alkene, okay, you're going to be in this 5-ish region. If you're hanging off a benzene, you're going to be in the 7. If you're going to be the hydrogen of an aldehyde, right? So it's similar to this, but now you're adding on to it the fact that there's an oxygen here, so it's even further deshielded. It's actually in this 9 region, and then a carboxylic acid is all the way down here above 10. And so these in particular are good distinctive groups to be able to these are fairly diagnostic for where it is, for what the hydrogen is going to be hanging off of. Okay, these are a little bit tougher because you need to sort of puzzle it out. Sort of below 1.5, it's pretty much just alkane stuff. But in the sort of 2 to 4 region, you kind of gotta do some reasoning. Okay, use some reasonings to be able to do that. Now, a typical sort of machine is going to be being able to it's usually typically measured in field in magnetic strength, and it's typically done as a megahertz. So the higher the megahertz, the more the stronger the magnet. Okay, and so if you get a the 60 megahertz one we have in the organic chemistry lab, it runs in that $50,000 to $75,000 range. Okay, the one we bought a few years ago, that was a 400 megahertz machine, was about $350,000. If you start going up even higher field strengths to 600, you're talking about well over $1 million. And now we're getting to the point where I think the highest field strengths are 1100 megahertz, something like that, and those would be tens of millions of dollars. Okay, something like that. So why do you need that? Okay, you need that for the it's like megapixels on a camera. Okay, so if I take a picture with so I have an older phone, I have an iPhone 7. So if I take a picture of something, right, take a picture of a flower, right, you're going to be able to tell that that's a flower. Okay, you can be able to. But if I do one of the new the brand new iPhones, a much better camera, I take a picture, it's still going to be the same picture of a flower. However, the resolution is going to be much better. So if I want to zoom in, I can see a lot more detail. Okay, so that's what's going on here. It's not that the signal is going to be very similar to it, but the stronger the magnet, the better the resolution that you're going to be able to use to see. Okay? So so if you look at this, and so if you're comparing a 40 to a 60 to a 300 megahertz machine, all of the signals are at the same place. Okay, so the computer's going to be able to actually align this. So if you have a signal that's 5.5 on a 40 megahertz machine, it's still going to be at 5.5 ppm on a 300 megahertz machine. So notice how all of these line up. Okay, so you don't have to account for the field strength. The computer does that. Okay, the difference, however, is when you compare a 300 to say a 60 megahertz. Notice how there's a lot finer details. So in this one, these peaks are all smashed together. But on the 300, you see these two distinct sets of peaks, sets of signals. Okay, that can become So this is why. You pay the extra money to be able to get this resolution, to be able to see the fine detail. And we'll talk about why that's important in a minute. Okay, but the signal itself, if it's at 5.5 on a 60 megahertz machine, it's still going to be at 5.5 in a 600 megahertz machine or a 1000 megahertz machine. It's still going to be at that same point. And so this can be important if you're looking at, say, a protein, with a lot of proteins on, with a lot of hydrogens on it. This is an NMR spectrum of a protein in a 600 megahertz machine, and so trying to get these fine details is going to be difficult. Okay, so typically if you're doing really high field strength, it's these sorts of problems you're trying to solve because you need to get that ultra fine resolution. And so this is sort of just talking about, this is in a slightly wrong spot. This is just talking about the fact that being near an electronegative atom causes it to shift to a higher number downfield. The other thing that happens is this, with benzenes, they're unusually high numbers, right? So downfield quite a bit for what they are. And the reason for that is the fact that, remember with a benzene, right, you've got this electron cloud that can go all the way, the p orbitals are sort of smeared all the way around. Well, that means the electrons can whirl around. Okay, and anytime you have an electron or a charge moving in space, you create a magnetic field. Okay, so it's going to make an extra big magnetic field. So it's going to feel extra, not only your external magnetic field, but also the giant magnetic field caused by the electrons moving around here. So so it's feeling a lot of magnetic field. So it really shifts it down, the signal down in like the 7 region, and so that's very diagnostic. You get the same effect, although on a not quite of a large magnitude, with a carbon-carbon double bond. Okay, and so it creates this large shift more than you would expect. Okay? So that's why it's in this sort of 5 region. These hydrogens here would come out right around 5. Now, one of the things that happens is, if you look at, for hydrogen NMR, if you look at the area under the peak here, okay, that's going to be relative to how many hydrogens are on there. Okay, so this signal from the blue hydrogens gives this area. Okay, the one in the red, these are all equivalent because you can rotate around the bond, okay, to get these all in the same position. So this signal is representative of these 9 red hydrogens, but the area under the curve is actually 3 times what it is for this one, because this one is dealing with 3 times as many hydrogens. So what they used to have to do is print these things out, take an X-Acto knife, and cut out the peak as well as they could, and get a weight. How many milligrams does this peak do? Right. So let's say this one was 4 milligrams. Okay. So then you'd cut out this peak. Get it cut out on an X-Acto knife. Cut out the paper part. That's this one, and that would be 12 milligrams. And so you would know that this one is 3 times of this one. So, but now one of the things they'll do is they'll do this signal right here. You'll see this sort of squiggle right here. This one is telling you the height is proportional to the area. So this signal is a third of this signal, right? So you can think of, so this one can get here, here, here. So that means this signal must be 3 times, dealing with 3 times as many hydrogens as this one. Okay? So lots of times, and so just like a CH2 would be twice as much area as a CH. Now, you don't want to look at peak heights, you want to look at area, because sometimes they can spread out a little bit. So you have to be careful with that. But what it ends up giving you is giving you a ratio. Okay, so if you have a sample, is C6H10, you have 3 signals, and the first signal integrates to 1, the second one to 3, and then the third signal integrates to 6 hydrogens. Well, we know that the ratio of those peaks is 1 to 3 to 6. Well, that makes sense because there's 10 hydrogens here, and so we can account for all of these. If instead we had, sort of a signal like this, right, and this would integrate to 1.5, this one would integrate to 2.5, and this would integrate to 4, that doesn't make a whole lot of sense. How do you have a half a hydrogen? Okay, so what we would do is as long as you do it to everything, right, you can multiply the ratios by 2 or 3 or 4 or whatever. Okay, so that not only do they become whole numbers, but also they account for, if you add these up, it goes to 16. Okay, just like 1/2, that proportion is the same as 2/4, which is the same as 3/6, which is the same as 4/8, right? So for that, as long as you do it to both sides, you're fine. And if you do it to all of them, you're fine. Okay? So most of the time you're going to see it like this, but sometimes on standardized tests they'll throw something like this at you, and you just need to multiply. Make sure you multiply it so the proportion is the same, but you can account for all the hydrogens. Now, splitting. Okay, so integration will tell you how many hydrogens are represented by that signal. But it turns out that the neighborhood, right? So the neighborhood is telling you where along this signal you get the signal occurs. But also the neighboring hydrogens, okay, will actually cause the signal to split into multiple peaks. Okay, and learning it and looking at how it splits will tell you how many neighbors there are. Okay, And so for hydrogen here, so we have this what's called n+1 rule. So it's neighbors, neighbors plus 1. Okay, so if you look at carbon 1, it has 1 hydrogen, right? So this would integrate to 1 hydrogen. Okay, how many neighbors does it have? Well, you look over here on the neighboring carbon here, right? And it has 2 neighbors. So that must mean, so n+1 equal 2 plus 1. So that means it would be split into 3 different peaks. And this one we would call this a triplet. So the signal that represents this 1 hydrogen, okay, is split by its 2 neighbors into 3 peaks, because it's neighbors plus 1. For carbon, for the carbon 2, these 2 hydrogens are equivalent to each other. So this signal would integrates to 2 hydrogens. So the area under this peak is twice what it is under here. But here the neighbor n+1 is just, it only has 1 neighbor, right? This red hydrogen here. So it's be 1 plus 1, so 2. So it gets split into 2 peaks because there's only 1 neighbor. It's not the fact that it's a CH2. No. It just means it has 1 neighbor to it, 1 neighboring hydrogen. So we'd have a triplet, a signal that would integrate to 1 hydrogen, but it's split into a triplet. This signal here integrates to 2 hydrogens, but it's split into a doublet because it has 1 neighboring hydrogen to it. Okay, so by looking at the integration and the splitting pattern, you can tell not only what's on the hydrogen, on that carbon, but how many hydrogens are on the neighboring carbon. Okay? And so if you have, if there's no neighboring hydrogen, so let's say it's just a carbon, or it's an oxygen, or it's something else that doesn't have a hydrogen on it, you're not going to have any neighbors. So that means that the n+1 would be 0 plus 1, so it would be 1, and we call that a singlet. 2, if you had 1 neighbor, you would get a 2 out, so it's a doublet. If you have 2 neighbors, you get a triplet. 3 neighbors, it's a quartet. 4 neighbors, it's a quintet. 5 neighbors, it would be a sextet. 6 neighbors, it would be a septet, and so on. Okay, if there's a whole bunch of them and they all get kind of smashed together, we'll talk about this in a minute, this would be what's called a multiplet. And this one we don't know, it's just so messy that we can't tell. Okay, so this comes up on the homework, so it just means we don't know. Okay? I'm not going to do that on the test, but I do want you guys to be aware of it. Okay. Now, one of the things is that equivalent carbon or equivalent hydrogens don't split. Okay, they act as a set. Okay, so here you would get so these red ones. Oh, let me get the colors right. So these hydrogens would act as a set, and these blue hydrogens would act as a set. Okay, so the red ones are essentially acting like CH6. Okay, so it's going to integrate to 6 hydrogens, but looking at the neighbor would be the ones in blue here, and so it would be n+1, right? So it would be triplet. If you're looking at the CH2, it would integrate to 2 hydrogens, right? But it has 6 neighbors. It's got the 3 on this side and the 3 on this side. So it has 6 neighbors to it. So the 6 plus 1 equals 7. So it would be a septet. So this would be a septet. Okay, and this would be a triplet. Okay. Now, how many neighbors would this have? Okay, so remember the rule is, right, n+1. Right, so for this first one here, right, so n+1 equals 2, right, so that means n would have to be equal to 1 neighbor. For here you've got 1, 2, 3, 4, 5, right, so n+1 equals 5, so that would be n is equal to, so neighbors would equal 4. Now for this one we only have the 1, right, so that would be n+1 equals 1. And so for here, we wouldn't have any neighbors. Okay, so it would just be like an oxygen or a C double bond O, or a carbon that has a bunch of chlorines on it or something like that. Okay, something that doesn't have any hydrogens immediately adjacent to it. Okay. Now again, for these, okay, so for this one, right, it turns out that these 4 here are chemically equivalent to each other. So if you were to flip it and flip it this way, or rotate it, however, these 4 hydrogens, because they're chemically equivalent, and they're on different hydrogens, but they're next to each other, they don't split. It just gives a single signal, right? Because here, there's no hydrogens, right? No H's here or here. Oops. Right? So so for here, the neighboring hydrogens would be right there. There aren't any hydrogens there, right? It's just carbons. Same goes with these guys, right? These and these, the blue ones are equivalent to each other, right? Because if I were to just flip it over, right, they would be equivalent. But again, they're looking at these 2 carbons here as their neighbors. There's no hydrogens there, and so that's why it gives a signal. Right? But these would integrate to 6 hydrogens, these would integrate to 4 hydrogens. Right? These 6 here, these 4 would be here. Now if you broke up the symmetry, then if you put a chlorine down here, then what would end up happening is these 2 would be equivalent, these 2 would be equivalent, and then you'd have a CH3, so you'd have 3 signals. Okay? And then these guys would get split by these guys, and these guys would get split by here. Now, one of the things with OHs and H, we really haven't talked about this much. Their splitting can get a little weird, okay? And it's really solvent dependent, okay? Because what's going to happen is, depending on the solvent, sometimes it can get, because they're acidic, they can exchange with the solvent. So usually when you run these things, you run these in deuterated solvent, because deuterium is not, because it's blind under hydrogen NMR. Like that, and so it can exchange off of there, and so you can get it, because the exchange is faster than the NMR can read it. You will sometimes get these sorts of like low peaks here for these NHs, and then these guys don't always get split by it then. So this one doesn't really get split because it's not around. Sometimes you see it, sometimes you don't. There's kind of not a good rule of thumb for that, so be aware. Now for coupling constants, what we're looking at is we're looking at the gap between this gap here and this gap here, okay, as well as this gap here, or this gap here, this gap here, here and here. If you look at that gap, okay, that gap will tell you what it's next to. Okay, so if you look at coupling constants, so if 2 things have the same coupling constant, that means those hydrogens are splitting each other. Okay, so these 2 hydrogens are splitting each other, and these 2 hydrogens are splitting, or these 2 sets of hydrogens are splitting each other. Okay, because these have similar coupling constants. We can tell that. Okay, and I don't know why it's represented by a J, but it is, for whatever reason. And so if you look at this, and the computer comes in and tells you what the coupling constants are, what you'll find is that these peaks and these peaks here are splitting. And then these peaks, these guys are splitting. Okay, so these guys here are splitting, and these guys here are splitting with here. Excuse me. Okay, so that's one of the things you can use as extra pieces of information to tell you who's next to what. Now, one of the things is, so far we've had it just splitting on one side, but the problem is molecules, as they get more complex, okay, you can have non-equivalent hydrogens on either side. Okay, and so what that happens is you get these complex splitting patterns. Okay, and so for this one, right, remember these three are all different. Okay, these three hydrogens are all different. Well, what's going to happen is if you look at this one, this hydrogen here is going to split the signal into a doublet, right? Because there's only one hydrogen there. And then this hydrogen here is going to take that signal and split it again to another doublet. So what the signal is for this red hydrogen would be what's a doublet of doublets. Okay, so it'd be two doublets right next to each other. Okay, so the first one would split it into a doublet, and then this one would split it again into a new set of doublets. So you get a doublet of doublets. Okay, and so if you look at, say, this one here, okay, if we look on this side here, right, this one, if we ignore this side, okay, if we look on this side, right, these three are going to split that signal into a quartet, right? So n plus 1, right, 4 plus 1, right, so it'd be a quartet. If we ignore this side, right, this would be these guys here would split the signal into a triplet, right? So the signal for number 3, would be a quartet of triplets, or it would be a triplet of quartets. You really can't tell. All that means is the of, whenever you see that, is that you have something on one side splitting you into a quartet, so you have a CH3, and then you have something on the other side that's splitting it to a triplet, which would be a CH2. So you can figure out, all that means is that you've got things on either side that are splitting it. If we look at number 2, right? If we look at number 2, right, this is going to split it. If we ignore this, right, if we ignore the aldehyde, right, this is going to split it into a triplet. If we look on this side, right, we ignore that, right, this one only has one neighboring hydrogen, right, it's right here, right, it's still attached to that carbon. So this would do it into a doublet. So this is how you get the, right, doublet, a triplet of doublets, right? That just means we have a CH2 on one side and we have a CH on the other. That's all that means. So you can have a triplet of doublets of quartets, or a triplets of quintets to something, I don't know. You can have all sorts of crazy stuff. So you can have, a doublet of doublets. So you can have all sorts of craziness. Okay. So but all the of means is like on the other side. So we have a triplet, so we'd have a CH2 on one side, and then on the other side we have a CH. That's all that means. It's not anything wild and crazy. It's just adding an extra bit of information on, well, what's on the other side. That's it. Okay, so how do we solve a hydrogen NMR? So I'm going to walk through some steps. So this is one of the first. This is before you even really dive into it. It's things that you'll want to take a look at. Okay, so one of the first things is you're almost always given a chemical formula. Okay, and so when you do that, you can actually run a quick DOU check on here. You can just run it through this equation, and you can get some information. Do I have a pi bond? Do I have a pi bond? Do I have a ring? Do I not have either one of those? Having a 0 is really important, because then you know, oh, it's just going to be a straight chain. Okay, and so that can give you some information as to what to expect. You can also look at how many peaks there are. It doesn't match up with the number of carbons, right? So if you have 5 carbons and you have 5 signals, now it's more of a rule of thumb, right? And we'll actually have an example where we don't have that. That means that each one of those carbons is probably not going to be equivalent. Okay, but if you have, say, 5 carbons in your sample, but you only have 3 signals, well, there's a good chance that you've got you either have a couple carbons that don't have hydrogens, or there's definitely not all going to be, they may have some that are equivalent. So be careful with that. You can also look at the peak integrations. Okay, this is especially good with multiple choice tests, because what you can do is you can say, well, if I have if I have 3 signals, a CH3, a 3 to 1 to 3, well, I know I have a CH3 and a CH and another CH3. So you could get rid of any choice that has, say, a CH2 in it. Well, you can get rid of that one and that one, because or if it only has one CH3, we can get rid of that one, right? So we can actually, so integration is fantastic for knocking out things on multiple choice tests, right? But when you're actually having to solve the structure, right, it's good to know, good to check to see, make sure, can you account for all of the hydrogens? Okay, that's a good thing, right? Do you need to multiply that because you're just giving ratios? Okay, is there anything distinct for any distinctive regions, right? So particularly things like the aromatic, right, which are benzene, so right around 7, or aliphatic, right, alkanes, right, those are below about 1.5, or aldehydes or alkenes. Okay, just try to figure out, okay, is there any weird splitting patterns? Are there any singlets? Right, those are really valuable to look at. Okay, and if there's any coupling constants, so you can just kind of take a look at, sort of what, take a quick sort of survey the field before you really start diving into it. Now, there's a bunch of different ways that you can go about solving these things. I'm going to show you one, but what I would suggest is going in and figuring out a way of doing it that's comfortable for you, and then doing it the same way every time. That's going to make the process a lot easier, because you're not going to forget steps. Okay, so this is how I usually do it. Okay, so the first thing I'll do, right, just take a look, right, so we've got 3 carbons, we have 3 signals. So that's we're probably going to have 3. We're not going to probably have 3 carbons that are equivalent. So that's okay. Okay. Now we have 5 hydrogens, right? So we have got 5 hydrogens here, right? We have 3 signals, a 3 to 1 to 1. So that we can account for all 5. Okay. Now these here in the 5 region, right? Those can be fairly distinct of being part of an alkene, but we'll have to take a look for that. Okay. So the first thing we're going to want to do is we're going to want to do a DOU calculation. And so if we run this again, we're going to get 1. So now we don't know at this point, is it a ring or if it's a pi bond. But we know that there's something in there. Okay, it's not just going to be a normal straight chain alkane. Okay, so that gives us a heads up. The next thing you're going to want to do is you're going to want to take a look at I usually look at the integration and splitting patterns. And so usually what I'll do is I'll say, okay, this guy here, this first one is a CH3. This one here is a CH2, and I'll usually circle it so I know what I'm talking. So we know what the actual signal is, and this is a CH. Right? And then you can use the splitting pattern to say, okay, what's next door, right? So we have a singlet here, so that means there's no neighboring protons. So this must be a CH3 next to say a carbon that doesn't have any hydrogens to it. Here we've got, because it's a doublet, that means that there's one neighboring proton, so it must be a CH. Same thing down here. So we have a CH3 next to something without any hydrogens, and each one of these CHs is next to something with a CH. Okay. So that's good. Okay. The next thing we can do is we can look at the chemical shifts. Okay. Now these guys here, the 5, okay, these are pretty distinctive of this region here. Okay, that's pretty much all that's there. So that would indicate that these guys are you have a double bond and it's coming directly off of it. Okay, so that's what these guys are. They're part of the it's this here. The other problem, so the other one for this too, this becomes a little bit more of a challenge. Okay, so first off, we know it's not a CH3 next to a benzene because we simply don't have enough carbons. The other thing you can do is, so even if you had 8 carbons, you could possibly have some that are benzene, but the problem is we only have 1 DOU. So in order to have a benzene, you'd have to have 4 at least, right? So we don't have enough DOU, so it can't be that. Can't be one of the, can't be next to a nitrogen because there's no nitrogen in the molecule, right? So it's not that. There's no sulfurs either. It can't be a triple bond, right? Because we only have 1 DOU, not 2, right? Remember, an alkene has 2 pi bonds, so it needs 2, so it can't be that. It can't be a C double bond O because we have no oxygen in the molecule, so it can't be that. And so it must be, all that's left is this. So this must be a CH3 next to an alkene, right? And we know it's a CH3 because of the integration. So it must be this guy here. Okay, so we can use some logic to figure out, it's next to this. Okay, and so now what we can do is we can start assembling these things. Okay, so there's a couple of different ways that we could do this. So we know we have a CH3, and then next to a C double bond. You know, these two next to an alkene, right? Because the DOU, right? We know we have a DOU, and both of these integrations would indicate that it's a you have a CH, and so have that, right? And so what we're missing is one thing here, one thing here, and one thing there, right? Because this has 3 red bonds. This one only has 2, so this must have 2 things on it. This one here, right? So we could put, say, a hydrogen here and a hydrogen here, and that would leave the bromine here. Now, does that make sense for what we're seeing? Well, the problem with this is if you look at this signal here, right? What we need is, it's a singlet. So this signal, right, would give a doublet, a 3 hydrogen doublet. That's not what we have. Okay, so it can't be this structure because it doesn't align with what we're seeing for the signal. This one would be, not only would this one be wrong, but this one would be wrong as well, because this would split it to a quartet and this would be a doublet. So you'd have a doublet of quartets or a quartet of doublets. We don't have that, right? So that signal is wrong as well. So it can't be this structure, right? So it can't be this structure. So how else would we do it? Well, what we would do is we would say, okay, well, we can't switch the hydrogen because that's not going to do you any good. So let's switch the positioning of the bromines. Okay, so here. And so let's put the hydrogen here and put the bromine here. Well, this makes a lot more sense, right? Because this one here, the CH3, right, is next to something that doesn't have any hydrogens on it. So that would give us our singlet. So what about these guys? Well, remember with alkenes, right, you can't get free rotation around this bond. Okay, and so that means these guys are not equivalent to each other. So they can split, right? They're on the same carbon, right? So if neighbors can split, well then certainly if you're non-equivalent on the same carbon, you're close enough to split. And so this one is splitting this into a doublet, and this one is splitting that one into a doublet. So that's where you get it. And so this has to be the overall structure of our molecule. There's only one way that we can make this all work. Okay, for this structure we have some problems. Yes, it's a potential structure for this, but it doesn't align with the signals that we're getting out. So it won't work. Okay? So it has to be this. Now if we wanted to do another one, right, so for here, right, so we have right, we have 5 carbons, we have 3 signals, so there's a good chance we're going to have some what is it, we may have some equivalents, right? We may have some that don't have bonds on it, or don't have any hydrogens on it, so we have to be aware of that. Okay, but we can, right, so 6, 3, 1, right? Okay, so that equals the 10, so we're good on that. Okay, we can account for all of the hydrogens. Okay, so we run the DOU. calculation, so DOU, right? So 2 times the number of carbons, which is 5, right? Plus 2. We don't have any nitrogens, right? We don't have any halides. We do have 10 hydrogens, right? All divided by 2. Now there is an oxygen, but that's not part of the equation, so don't put it in. Okay, so this ends up being 12 minus 10, right? So it's 2 over 2, so it's 1. So we have 1 degree of unsaturation. We don't know if it's a ring or a pi bond. We don't know that yet, but we need to take that into account. Okay. So now we're going to look at the integration. So how do we get 6 equivalent hydrogens? Right? We can't stick 6 hydrogens on a carbon. But what we can do instead is we can have this be 2 equivalent CH3s. Okay, and then this would be a CH3, but this would be distinct from this CH3, and this one would be a CH. Right. Now, okay, so that's what the integration is telling us. And so if we look over here, saying, okay, so the doublet, right? So remember, this is n plus 1, right? So what plus 1 is equal to 2? Well, that must be a CH. The singlet, right? What plus 1 equals 1? Well, 0. So that must be a carbon that doesn't have any, or something. A carbon or something that doesn't have any hydrogens on it. And then here, this is a septet. So, n plus 1 equals 7. So that must mean it must be a 6 hydrogens. Well, this would be this mythical CH6. Right, which is probably going to be, right, 2 CH3s, 2 equivalent CH3s. Okay. So we have the parts. Okay, so we have two equivalent CH3s that are attached to a CH. We have another CH3 that's attached to a carbon that doesn't have anything. But we also have a CH that's equivalent to attached to 2 CH3s. So these are probably right next. These are probably, one looking at one way and one looking at the other, but these are probably the same bits, just looking at it from right to left and left to right. Okay. Now, next up is the chemical shift. Okay, so we have the 0.95 is probably just going to be an alkyl. The problem is going to be the ones that are in the 2. Okay, so it can't be the benzene, because we don't have enough. Not only do we not have enough DOUs, but we also just don't have enough carbons. Okay, we don't have any nitrogens, we don't have any sulfurs, we don't have enough DOUs to be an alkyne. Okay, so the problem is we do have an oxygen, okay, but we could also do this. Okay, so it's going to be some sort of C double bond O, or C double bond O, C double bond C. So that takes account our DOU. So we know it's probably not going to be a ring. Okay, so these can be either a CH3 next to a C double bond C, or a CH3 next to a C double bond O. Down here, this could either be a CH next to a C double bond O, or it could be a CH next to a C double bond C. Now, we can't really tell, so we need to make an educated guess of which one it would be. Okay. Now, it could be either one, but one of the things about this is that if you have an alkene, what's most likely going to happen is you're going to have at least one hydrogen on that alkene be around. It's not going to be completely substituted. And because of that, you would expect there to be at least one hydrogen, say here, that would be that would give a signal right around 5, right, for that alkene, right? So we would expect a signal if it was an alkene. If our stuff was next to an alkene, we would probably have at least one hydrogen that's hanging off of it, which would give a signal that would be over here. We don't have that. Okay, so remember, sometimes what's not there is just as important. And so since we don't have anything here, then what that means is that it's probably not this, because we don't have any signals here that would indicate we have any hydrogens on there. So most likely it's going to be a C double bond O for both of these, because we don't have any of these, because we don't have any signals for that. So this is probably the best place to start. Okay, and so what we can do is we can say, okay, well, we have a CH3 next to a C double bond O, and then here we have a CH next to a C double bond O. Well, we don't have two, we only have one oxygen. Oh, let me put this in a slightly different color. Ooh. So we have a CH next to a C double bond O. We don't have two oxygens. So this is probably the same CHO, right? So probably what we have is we probably have here a CH like that, right? So a CH3 next to a C double bond O, and we have a CH next to a C double bond O. So it's probably like this. And then what do we have hanging off of the right? Because we have two bonds that we haven't accounted for. Right? Well, what's next to it? Well, it's the CH6. Ah, it's these two equivalent CH3s, which would be here and here. So this is a potential structure. Does this make sense? Okay, well, we have a CH3, right, that's next to something that doesn't have any carbons on it. Okay, that makes sense. We have a CH that has that's next to a CH6, right? So that would be here. And then we have the CH, the CH6 here, which is next to a CH. Well, this makes a whole lot of sense. This makes sense with the chemical shifts, right? Both of these are, in the 2s. These guys would be, the greens would be the alkyl. So that's probably what it's going to be. So this makes sense for all the information. So this is our structure. Okay. And we didn't need to try having a double bond here. Okay. So here's our structure. Now, one of the things that you can do is if you're trying to look for something like stereochemistry, you can do some really complicated experiments, and you do what's called 2D. And what you do is you align. In this case, it's two hydrogens, and what you're looking at is, so along this diagonal here, you're just talking about you're comparing this to here. So this 4 and this 4, right? So this signal here just goes to there and there. Okay, so that makes sense, right? Because those are the same. But what's happening is, what that's also saying is that this signal here is also interacting with this. And so here, so these guys, so that means these guys are interacting. Okay, so these guys are interacting. But also these guys here, because there's a signal here, you go down, these guys, and then here. So that means these guys are also interacting. So what's happening is this one, the signal at 4, is also interacting with this signal, like this on one side, and then these guys on the other. And so you can use these to figure it, to help to give more information about how the hydrogens are positioned more accurately. You can also do this where you have a hydrogen on one side and a carbon on the other, which we'll talk about in a second. And what this does is it says, okay, if we get a signal here, then that means this signal goes with this carbon signal down here. This hydrogen signal are associated with this carbon. This signal here, these hydrogens are associated with this carbon signal. So this carbon has these hydrogens on it. These carbons have these signals, are part of these signals here. Okay, and so you can sort of figure out who's with what. So now for carbon NMR, okay, so one of the problems with carbon NMR is that if you look at the carbon 12, which is approximately 99% of all the carbon in the planet, it does not have a magnetic nucleus, right? Because it has 6 protons, 6 neutrons. Both of these are odd. Neither one of these are neither one of these are odd, so it doesn't have a magnetic. Only the carbon 13 does, okay, because it has 7 neutrons. But the problem is it's only like 1% of the sample. So unless you actively put in carbon 13, make your molecule out of carbon 13, which you can do, but that you're not only about 1% of your the carbon in your sample is going to have a signal within your spectra. Okay, so what that means is that 99% of your sample isn't going to be the NMR isn't going to be able to see. So for hydrogen NMR, you only have to take 8 to 10, 12, 16 scans, and you can get a pretty good signal. For here, you have to take a lot of scans, and so this usually, not only are the scans longer, but you have to do thousands of them. Okay, because if you were to take one scan, you could maybe get these. Okay, but how do you know it's not just random noise? How do we know that's, is this, what about this guy here? Is that a signal? We don't know. These probably are, but we don't know. Okay, and so what we do is we take a whole bunch of scans. Okay, and then we average them. Okay, and what happens is all of this part that's random noise gets after you average it enough, it's going to go down to baseline. Okay, and this guy here, which will be down here, is just, as it turns out, just noise, and it's just these three that ends up being signals along with this one. And so it's sort of like thinking about if you play a game and you say, okay, I'm going to flip a coin, and so if it comes up heads, I give you $1. And if it's tails, you give me that $1 back. Okay, so after after 3, you may be up $3, right? So but if we do it 1,000 times, right, the law of averages is going to kick in, and so you're gonna win $500, but then give me back $500 as well. And so we're not going to be assuming it's a good coin. We're not going to, it's all going to average out to 0. Now, if I get, if I flip a coin and it's heads, I give you $1. And then if and then also if I flip it to tails, I give you $1. Because you're winning every time. You're getting signal every time. Okay, even though it's not a lot, after 1,000 signals, you're going to have $1,000, right? And so that's what's happening is each signal gives a little bit more. Okay, where there is supposed to be a signal, you're going to get a little bit. It's going to start to build up, and the baseline is going to be random, up and down, up and down, up and down, and so it's going to average out to 0. So you have to take scans, and so these carbon NMRs can take 6-8 hours to run. So because you need so many signals. The other thing about carbon-13 is the likelihood of, unless you put it there, 2 carbon-13s being right next to each other is astronomically low. And even if you do have a molecule that has it where the carbons just so happen to be next to each other, it's only going to be one molecule in billions of molecules, right, or trillions, or however you want to do this. So essentially what's happening is those are the only ways that we could split. So in carbon NMR, there's essentially, unless you actively put them in there, you're not going to get any splitting, because the likelihood of you having a lot of carbon-13s right next to each other is exceedingly low. So we don't have to worry about anything about splitting. Okay, but again, here we're going to be looking at equivalence, but here it's carbon equivalence. Okay, and so again, you can do the same thing where you draw in the molecules, and you can say, instead of the hydrogen substituting, you put the carbon substituting for X. And so for these guys here, for A, B, and C, there's no way that I can flip this molecule to make it look like this, because, right, it's at the end. But even if I flip the molecule over, then, the methyl groups will be on the other side. So these guys here will give distinct, the carbons for here, here, and here would give distinct ones. But these D, E, and F, right, so these carbons, if you rotate around this bond, right, I can make E and F by rotating around the bond look like D. So these 3 carbons would give a single signal. So you get 4 signals out. One for A, one for B, one for C, and one that would and another signal that would give a D, that would represent D, E, and F carbons. Okay. The chemical shift chart, Okay, it's going to be a little different because here the ppms are a little bit spread out, but the trend is very similar. Okay, so if you have alkyl stuff, you're going to be way down here at low numbers. As you add electronegative things, you're going to get moved farther and farther this way. Benzenes, if you're on a double bond, you're in this region here. If you're part of a C double bond O, just like if you're part of a carboxylic acid or an aldehyde, right, you're way down here. Same thing here. If you're a carbon that's part of a C double bond O, you're above 150. Okay, so again, I'm going to have you, I'm going to give you this chart, and you just need to know how to utilize it. So if we're looking here, right, so carbon A would be this one here, right, because it is it's part of a C double bond O. C would be here because it is next to, right, so it is next to a C double bond O, so it's next to something that's somewhat electronegative. Okay, so it's going to be around in this region here. Okay, these guys here, B, D, and E, are down here in the normal sort of alkane, so it's pretty distant from that oxygen. Okay, so these guys here would probably still be considered alkyl, but it's a little bit closer to this double bond, so it's going to get shifted a little bit down. So this one is just solvent. So deuterated chloroform is one of the ones that's usually used. So with that, so it's nice because it has deuterium instead of hydrogen, so it doesn't show up in the hydrogen NMR signal, but this carbon here shows up. So not a big deal. We just account for it. So the other thing is, for integrations, they're essentially meaningless. Okay, so we can't really, just like we would say, like it's a CH, it integrates to 2, so it must be CH2. We can't really do that with carbon. Okay, just because something's higher doesn't necessarily mean there's more carbons associated or hydrogens or things like that. There's other ways that we can do that. Okay. The way that we do that is what's called the depth experiments. Okay, and so if we have what's called the broadband, okay, that's where we're looking at all the different carbons. Okay, it looks at all of them. Okay, it shows all the carbons. Okay, we're going to get signals for here are all the signals. Okay, so these guys down here, these are part of these 4 signals here, right? 1, 2, 3, 4, right? So here's a signal, right? These carbons are equivalent, right? These carbons are equivalent, and then this one is its own, right? Because if you flip the molecule, right, these would go here, right? So like if you took a coin and went like that, and now it's spinning, that would make one of these signals is for these two, another signal is for these two, and then a signal for the green and green signal for the orange. Okay, and then these two would be these guys over here. So it turns out that if you run it what's called a DEPT-90, and we can do this on our NMR, it works really well, it only shows CHs. Okay, so what we're going to see is we're going to see these guys, right, because these are CHs, and these guys, which are CHs. Okay, and that's all that's going to show up. If we run a DEPT-135, if we get a positive signal out, okay, it could be either a CH or a CH3. We don't know. But we do know that if it gives a negative signal, and it's really weird, it goes below, it's a CH2. So we know these are always CH2s. Those are really simple. Those give a negative signal. If we have a signal that doesn't appear in either one of the depth experiments, oh, that's right. We're going to also see. So the reason why we have a third one here is because this one also has a hydrogen on it, right? So we get 1, 2, 3. So those are those 3. Right? So those are the 3 CHs. So we see those 3 because the CHs appear. We have a CH2 in our molecule, so that's negative, and then we also have a CH3, so it's going to be a signal here. But what about, right? So remember, our molecule looks like this, right? What about this? What about this carbon here? where was its signal? Well, we only saw it in the broadband. We didn't see it in the 90 or the 135. The reason for that is you have to have a hydrogen to be able to see it. So if you see it in the broadband, but you do not see it in either one of the depth experiments, we know that that signal must represent just a C with no hydrogens on it. Now, so here's the question. So how do you know if on a 135, if it's a CH or a CH3? Well, this is going to show up in the DEPT-90 experiment, right? So we know from this experiment that these guys here are CHs, because it's only CHs here, but nothing here, right? So that must mean that this one must be a CH3, because if it was a CH, then it would show up here, but we don't, right? It shows up here, so it can't be a CH because it's not in the 90, so it must be a CH3. If it doesn't show up in any of the experiments, it must be a C. All right, so no carbon signal in depth in either one of the depth experiments, 90 or 135. Okay, so how are we going to solve this? Okay, how do I do this? Okay, so first thing to do is this is how an experiment thing would look on the exam. So you have the formula here. You've got your broadband. So these are all of the signals, and then you've got the DEPT-90 and the DEPT-135, both the positive and the negative. Okay, so these are the total signals, and these are what you get from the DEPT-90, 135. So the first thing to do is to just take a look at this. Okay, we've got 6 carbons, but we only have 1, 2, 3, 4, 5 signals in the broadband. So that must mean that 2 of these carbons are equivalent to each other. Okay, it can't hide under something that doesn't have a H on it, right? We would see that carbon. So if we're not seeing, if they aren't, if the number of signals doesn't add up to the total number of carbons, that must mean 2. Some of these must be equivalent to each other. Okay. So you have to take that into account. So if we run a DOU check, okay, we run this, right, so C6H12, right, we run this and we're going to get a DOU of 1, right, so there's 6 carbons, right, so it'll be 12 plus 2 is 14, don't have any nitrogen highlights, but then we subtract the 12 hydrogen, so that ends up being 2 over 2, so it ends up being 1. So we need to account, is there a ring, is there a pi bond? We don't know. This should be, well, actually, yeah, it has to be a carbon-carbon bond. It can't be a CO bond, right? Because it's right, there's no oxygen, so it has to be either a carbon-carbon double bond or a ring. Next up, we're going to use the depth experiments, right? So what we do is we say, okay, there's a hydrogen, right? So we know the DEPT-90 has to be a CH, right? So we know that this is a CH, right? This is a CH, and this is a CH. For the positives, it could either be a CH or a CH3, okay? But we already know that, right, this is a CH, right, and this is a CH, right, because it's up here. So that makes this one be a CH3. Because it doesn't appear in this, we know it's not a CH, so it has to be a CH3. Now the negatives are easy because they're CH2s, and so they're here and here. Okay. Now we don't have any that don't have any signals on it, right? We can account for all of, we don't have any ones that don't appear in here. So that means we don't have any C's without carbons on it, or we don't have any, or C's without hydrogen. Okay, all the carbons have at least 1 hydrogen on them. Now, here, so what are we missing, right? So if we add these up, okay, so if we add up the CH3, right, the CH, the CH2, this CH2, and this CH, right? If we add those up, we can account for 5 of the carbons, right? 1, 2, 3, 4, 5. And we can account for 4, 6, 8, 9 hydrogens, right? So 3, 4, 5, 6, 7, 8, 9. What are we missing, right? We're missing a CH3. So where did it go? Well, that's probably going to be, because remember we only have 5 signals. So this would suggest that we have 2 methyls. And so what ends up happening is we have 2 of these. Now if you had 2 CH3 signals, right, you may not necessarily know which one is which. But for right now, we only have 1 CH3. So the easiest way to do that is say, well, what if we have 2 of these? And since they're equivalent, they're going to be, that peak would represent 2 CH3s, right? Because if they would be equivalent to each other. So this is a good check after you've assigned these to say, have I counted for all of the carbons and all the hydrogens? Well, no, we haven't. We're missing a CH3, a carbon and CH and 3 hydrogens if we just add these up. So that must mean that, these guys here are hiding under another one because they're equivalent to each other. So be careful. Okay. So if you look at the chemical shifts, right, these guys here are in that alkane region. Okay, so you look at the carbon NMR shifts, right? So below 50 is just regular alkanes, but these are alkanes, but they're shifted closer to something that might be electronegative. Okay, these guys here are in alkenes. Okay, because that's what's in this region. You could also, there's some sort of double bond. It could technically be a benzene, but the problem is we don't have enough carbon. Well, we don't have enough DOUs to be a benzene. Okay, so it must be an alkene. Okay, so what do we know about this? Well, we know that there is a right, carbon here, right? On one side, we have a CH2, and here we have a CH. Now, what we can find from this is the fact that this carbon has all 4 bonds accounted for. So we can't extend the chain this way, but we can this way, right? Because only 3 bonds have been accounted for. So that must mean we must need to extend the chain out here. So that means this alkene is at the end. So that must mean that we have a the rest of these carbons, the rest of these 4 carbons must be hanging off of here, and they have to be in a line, right? So that because we've already burned our one DOU to make the alkene, right? We can't have a weird ring or anything else like that because we don't have enough DOUs to do that. So we could do, so there's a couple of different ways we could try this. We could try doing the, the CH here and then the CH2, but then we'd also have to put the CH3s here and here, because that's the only way we could do that, because we would have, so we don't have too many bonds. But then these guys are not equivalent, these CH3s are not equivalent, right? Because this one would have, we don't violate, having more carbons on there than carbon having more than 4 bonds. So it can't be this structure. So let's try this again. So let's try it this way. And so now let's try, right, let's try putting a CH2 here, and then the CH. Okay, because we can't have the CH3 in the middle because that's its 4 bonds. So now we can put CH3, CH3. Aha! These carbons here are equivalent to each other, right? Because I can just rotate around that bond and flip the molecule like that. And so this is our structure here. That's the only way that it makes sense, given the information that we have. Okay. Good luck.